Alright, there I was. I was a young man, 19 years old, driving through Montana, heading to a friend's wedding. And I come across this bend in the road. On the sign it says danger, slow down to 25 miles per hour. I'm young, I'm confident, I think my car can handle anything. I'm zimming along at 70 miles per hour. And there I see it, a cliff face, staring in front of me with 3 wooden crosses. I slam on my brakes, and I barely make it around the corner with my blood at my feet and all my equipment on the right side of my car. Everything is shifted over, but somehow I made it around that corner alive. Now, today we're going to talk about curvature. And curvature is something every one of us has experienced in our life. If you're driving in a car and you're going around a corner, you're experiencing curvature. Another name for this is called tightness. So we're going to take a look at how we can find this curvature or tightness mathematically. So let's see here. Let's take a look. So again, we're driving around a car. We're driving a car around a curvy road. Now, the tighter the curve, the more difficult the driving is. As I'm driving down this road, it's a windy road, of course, because it's a mountain road. But then I come across this big curve and the big bend in the road, and that's where I barely made it out alive. In math, we have a number for this called K, and we describe that as curvature or tightness. This is actually the Greek letter kappa, but sometimes we just call it K, and it's okay. So how do we define a number using curvature? Well, we start with the very minimum. A curvature of 0 means basically the road is a straight line. So something that's a straight line has 0 curvature. And the more tighter the curve gets, in other words, the tighter that curve gets, the higher kappa becomes. If the curvature is large, that's what this says, then we have a very sharp bend. I am pretty sure that curve in Montana had an infinity for its curvature. I'm barely alive. Now, we can define curvature with the relationship with the radius of a tangent circle. So if I think of a circle at a point tangent to that circle is going to have a radius. Well, kappa, or the curvature, is an inverse relationship, 1 over r. So what that says is if we have a larger radius, for example, if I have a circle tangent here, if I drew a tangent circle to this graph, if I have a larger radius, I am going to have a smaller curvature. The smaller the radius, the tighter the curve, because the bigger the curvature. If I drew my tangent circle here, it's going to even have a smaller radius. So the smaller the radius, the larger the curvature. Now we can also use this equation to find radius. So I can just solve r is 1 over k. We're going to talk about that in just a few moments. So how do we get curvature mathematically? Well, the math behind it is kind of complicated. Well, it's not terribly bad. But there is a problem which we're going to talk about here. So if we let the unit tangent vector, if we let t of t, be the unit tangent vector of a function, then we can define curvature as the rate at which the unit tangent vector changes with respect to arc length. So we're basically looking for the derivative of the unit tangent vector with respect to arc length. Now, hopefully we kind of see a problem with that, because arc length is a function itself, is also another function. So when I'm describing the path of my object, for example, if this is my car, I'm going around a corner, at this point, right, there's my tangent vector, and I want to find out what is the curvature as we change to another point. So I call this point Q. My second tangent vector. I want to find out how this path is changing. And remember, this is the change of the arc length, s of t. So when we describe this path is really not r of t, but r of s. And that's the problem right here. So in order to get the arc length, in order to get the curvature, we have to write a path in terms of arc length. And that's very difficult to do, which we're not going to worry about that here. We'll get that in a second. So if we let C be a smooth curve given by r of s, where s is my arc length, then the curvature, or kappa, is given by this equation right here. So that's my curvature, which is the change in our unit tangent vector. That's what this is saying. It's the change in the unit tangent vector with respect to arc length, where s is the arc length and t is our parameter. So what you kind of notice, this could be written where s, right, where s, because remember, s is a function of t. So you can kind of see that's going to get very confusing. So this is not very practical, as we said, since writing this in terms of arc length is typically impossible to do. So we have to come up with another way to do this. So we use chain rule. So as remember, t is a function of s by itself. Remember, t is a function of s. So I can use chain rule. So when I take the derivative of my unit tangent vector with respect to arc length, I can write this as chain rule, the derivative of the inside, t prime of t, times the derivative of the inside, which would be dt ds. So you might need to fix it in your notes. So that's my derivative of my inside, which becomes t prime of t, and ds dt is just r prime of t. So we have this formula right here. So we can use this to find arc length. So what this is really saying is that this is the magnitude of the change in the tangent vector. And that's what we can use to find that curvature. Now again, this does have a problem. We saw this when we did the binormal, the normal, and the tangent vectors. If the magnitude of r prime of t is constant, this is easy. We like it. We're happy. But if this is not constant, it's not very easy for us. So if we're looking at circles, the helix, and things like that, that's our spiral or lines, this is a very nice and easy formula for us to use. If the magnitude of r prime is constant, this is going to be really easy. So again, because this is still kind of cumbersome, t prime of t is typically still a mess. Instead, we can borrow the formula for the normal vector to get the curvature. Well, remember, so we can use, and when we did the normal vector, we said to get the normal vector, we would use, you might recall, to get the normal, we would do this, r prime of t cross r double prime of t multiplied by that magnitude, r prime of t, right here, and then we're going to multiply that bottom again by the magnitude of r prime of t. And then we get our formula here. So here's our formula for kappa. It is the cross product of r prime crossed with r double prime over the magnitude of r prime cubed. So, and this will work all the time. This will always work for us. Now, if they give us a function in rectangular form, in other words, instead of r of t, we're given like as a function of x, then to get kappa, or the curvature, we use this formula. The magnitude of the second derivative, the magnitude of the second derivative divided by 1 plus the derivative squared to the 3/2. And we'll see an example like that in just a few moments. All right, so go to part 2. We're going to take a look at a bunch of examples.